In our previous video, we discussed how to measure chiller efficiency. If the chiller's efficiency is found to be low, then we need to check the approach values of its evaporator and condenser. These approach readings help us pinpoint whether the issue lies in the evaporator or the condenser, and by correcting that problem, we can restore the chiller's performance. Before calculating approach value, we need to understand a few basic principles of heat transfer. Knowing this will make the rest of the explanation much clearer. Imagine we have a tank containing 50 liters of water. Now, take another smaller tank with 10 liters of water. We connect both tanks using a pipe. Let's assume we have two such setups. One object is at 50 degrees Celsius, while the other is at 10 degrees Celsius. We don't need to consider the surrounding temperature here. When we open the valve between the two tanks, water will naturally move from the larger tank with 50 liters to the smaller one with 10 liters. In simple words, water always flows from a tank with higher volume to one with lower volume. Similarly, when two objects of different temperatures are near each other, heat flows from the hotter object to the cooler one. When there's more water in the tank, the flow rate is faster. As the amount of water decreases, the flow rate also slows down. The same principle applies to heat transfer. The greater the temperature difference, the faster the heat moves. When the temperature difference becomes small, the heat transfer rate also drops. Water will continue to flow between the two tanks until the water levels are the same. Once both tanks have an equal level, the flow stops completely. Likewise, heat transfer between two objects continues until their temperatures become equal. Once both reach the same temperature, there's no further heat movement. This balanced state is known as thermal equilibrium. These are the basic ideas behind heat transfer. Now let's see an example that will help you easily understand the concept of chiller approach. Suppose we have a tank holding 50 liters of water. When the level drops below that, water is added automatically from a tap to keep it constant at 50 liters. So the level in this tank always remains steady at 50 liters. Every 10 seconds, water from this tank fills another smaller 25-liter tank. Let's find out what its approach value would be. The approach value equals the water level in tank A minus the water level in tank B. As mentioned, tank A always stays at 50 liters, while tank B gets filled with 25 liters. So, 50 minus 25 equals 25 liters. This 25 liters is the normal approach value of the system. If the approach value remains at 25 liters, it means the system is working perfectly. But if there's a blockage in the line and water flow becomes restricted, then instead of 25 liters in 10 seconds, tank B may only get 15 liters. Let's calculate its approach value again. Tank A has 50 liters, and tank B has 15 liters. That's a difference of 35 liters. So when the approach value increases beyond the normal range, it indicates that there's some kind of problem in the system. This same logic applies to calculating the chiller's approach value. First, let's determine the approach value of the evaporator. Inside the evaporator, there are coils through which refrigerant circulates. Water from the AHU passes through these cooling coils. When entering the coil, the water temperature is about 52.7 degrees Fahrenheit. The refrigerant surrounding the coil is at 41.9 degrees Fahrenheit. As we discussed earlier, heat always travels from a higher temperature object to a lower temperature one. So, heat transfers from the warmer water to the colder refrigerant. After this exchange, the water leaves the coil at 42.7 degrees Fahrenheit. Now let's calculate its approach value. The formula is evaporator approach value equals chilled water leaving temperature, refrigerant temperature. Substituting the values, 42.7 minus 41.9 equals 0.8 degrees Fahrenheit. If the evaporator approach value is below 3 degrees Fahrenheit, it means heat is being transferred efficiently from water to refrigerant. But if the value is higher than 3 degrees Fahrenheit, It indicates poor heat transfer. When heat transfer is inefficient, the cause could be scaling on the coil surface, or low refrigerant or water flow. Any of these can lead to a high approach value. Now, let's move on to the condenser's approach value. After the refrigerant absorbs heat from the evaporator water, it becomes vapor and travels to the condenser through the compressor. In the evaporator, coils are located at the bottom, while in the condenser, they're positioned at the top. Cooling tower water flows through these condenser coils. When entering, its temperature is around 90.1 degrees Fahrenheit. The refrigerant enters the condenser as a high-temperature vapor and must be cooled back into liquid form. As mentioned earlier, heat moves from the high-temperature refrigerant to the lower-temperature cooling water. This process lowers the refrigerant's temperature and turns it from vapor into liquid form. Since the refrigerant's heat transfers to the water exits the condenser at around 99.4 degrees Fahrenheit. It then goes back to the cooling tower, gets cooled, and recirculates to the condenser. Now let's calculate the condenser approach value. Condenser approach equals refrigerant saturation temperature minus condenser water leaving temperature. Plugging in the values, 100.6 minus 99.4 equals 1.2 degrees Fahrenheit. That's the condenser's approach value. Ideally, the condenser approach value should stay below 4 degrees Fahrenheit. Scaling inside evaporator or condenser coils can restrict water flow, heat transfer, leading to higher approach values. Scaling is generally more common in condenser coils than in evaporators. The main reason is that condenser water has higher temperature and mineral content, which increases scaling deposits. Also, when condenser water returns from the cooling tower, it's exposed to open air, allowing dust and debris to enter the system, which can block the coils. Typically, the condenser should be descaled once a year, and divine, while the evaporator needs descaling every 2 to 3 years. That concludes our detailed explanation of chiller approach. If you have any questions about this topic, please ask in the comments. If you found the video helpful, give it a like and share it with others who might benefit from it. And don't forget to subscribe to our channel, Intact Knowledge. Thank you.